Welcome to ISNTT 2021, which is being hosted virtually from NTT Basic Research Laboratories here in Japan. We really hope you enjoy the forthcoming conference with the outstanding program that has been put together for you. I would like to take this opportunity to give you a little background about our laboratory. NTT's Basic Research Laboratories, known as NTT BRL, is located approximately 50 kilometers away from central Tokyo and is surrounded by the rich nature of the Tanzawa Mountains. Our Atsugi R&D Center employs over 400 researchers working in various cutting-edge science and technology fields with access to state-of-the-art facilities. NTT BRL, as you can tell from its name, has its core mission focused around basic research and how the scientific and technological advances and innovations we discover can be used to enhance the well-being of tomorrow's society, create opportunities for future business, and of course, contribute to the expansion of academic research. Here within NTT BRL, researchers from a wide variety of disciplines spanning physics, chemistry, biology, mathematics, electronics, informatics, and medicine undertake groundbreaking research within the fields of material, physical, optical, and quantum sciences. NTT BRL consists of 3 key laboratories: the Multidisciplinary Materials Design and Science Laboratory, the Advanced Applied Physical Science Laboratory, and the Quantum Science and Technology Laboratory, all seamlessly working together. We have an impressive history of accomplishments with too many to highlight here. We can, however, introduce you to several of our latest research activities. Nowadays, electronic devices are getting smaller and thinner. For the development of future nanoscale devices, two-dimensional materials, including atomically thin conductors, semiconductors, and insulators, are considered promising building blocks. One of the promising materials is graphene. It is made of a single layer of carbon atoms arranged in a honeycomb lattice. Another example is hexagonal boron nitride. It has a honeycomb lattice similar to graphene, but is composed of alternating boron and nitrogen atoms. And this is molybdenum diselenide, an inorganic compound of molybdenum and selenium atoms. All these materials can be synthesized on substrates. Two-dimensional graphene, molybdenum diselenide, and hexagonal boron nitride represent the conductor, semiconductor, and insulator required for the electronic devices. Their further integration may lead to a new generation of nanoelectronics and nanophotonics devices with novel properties as well as high performance. Scientists at NTT Laboratories are now developing synthesis technologies of these materials on a large scale. Various characterization tools are involved to improve the material's quality to satisfy the industrial requirements. By combining several kinds of two-dimensional materials, prototype devices are also fabricated, including high-speed transistors, mechanical resonators, photodetectors, and plasmonic reflectors. NTT scientists will continue their efforts to explore the brand-new possibilities of these materials in both fundamental research and practical applications. This is an optical transistor. It can switch and amplify an optical signal using another optical signal. The parts that correspond to the gate, source, and drain in an electrical transistor are shown here. Let me explain how it works. The left part of the transistor is a nanodetector. Embedded in the center is indium gallium arsenide, which serves as a light absorber. When a light signal enters here, an electrical signal comes out. The right part is a nanomodulator. Indium gallium arsenide phosphide, which has an optical nonlinearity, is embedded in a tiny optical resonator. When an electrical signal is applied, continuous light is modulated by means of the nonlinear effect. We can make an optical transistor by integrating a nanodetector with a nanomodulator. A light signal entering the nanodetector is transferred to an output light from the nanomodulator. The transistor requires an extremely small optical energy per bit, just 1.6 femtojoules. This transistor can operate at 10 gigabits per second and produces an optical signal gain of 3.6 decibels. The optical transistor enables high-speed information processing that uses both optics and electronics. A new era will soon come when both the communication and processing of information are executed in the optical domain. Optical transistors hold the key to such a promise. This is a new computer called a Coherent Ising machine. The Coherent Ising machine can solve combinatorial optimization problems mapped onto the Ising model. There are just three main components: an optical fiber loop, a special optical amplifier called a PSA, and an electronic circuit called an FPGA. The PSA receives pump light and uses its energy to amplify light. Here, only light whose wavelength is twice the wavelength of the pump light is amplified. The PSA most efficiently amplifies light with phases 0 or pi relative to the pump phase. Here, we define the 0 phase light as upspin and the pi phase light as downspin. Now we get to the main point. With this system, pulses of pump light are input to the PSA. The PSA then outputs optical noise pulses with random phase states from 0 to 2 pi. The system starts computation with random phases. Using the measurement result of each optical pulse, a new pulse is created according to the spin-spin interactions of a programmed Ising model in the FPGA module, and the newly created pulse is injected into the original light pulse. As a result, the pulses are coupled with each other depending on the Ising model. The system repeats this process each time the light pulse circles the fiber loop. Due to the effects of the PSA, each pulse gradually approaches either 0 or pi phase state. When it is determined to be either 0 or pi phase state, the phase configurations can be a solution of the programmed Ising model. By using a network of optical pulses, the Coherent Ising machine can solve combinatorial optimization problems mapped onto the Ising model.
Hi everyone, I am Hideki Goto, the Director of NTT Basic Research Laboratories. I want to welcome you and thank you for your interest and support of our research activities. Within our laboratory, we run the open door policy, enabling us to bring early career researchers to work with us using state-of-the-art facilities, collaborating with many world-leading universities and research institutes. This provides an extremely dynamic environment to promote science and innovation at the technological leading edge. I hope we can also work together in the future.